Thank you to everyone for listening.
Great, thank you, Green Team. Any quick questions via the chat? I have one then. Could you give us a specific example of an idea that a Green Team would come up with?
Yeah, sure. So we were thinking about how the most important part of green teams is that the community itself gets to pick what ideas they want to implement. So an example of that could be like, say a faculty department, like the English department wants to have a green team. They could figure out how to incorporate ideas of sustainability within their own curriculum, within their own classes, or they could also try to think about maybe within their staff meetings, they want to start off the meeting with a green minute and talk about an environmental issue that they bring up at each new meeting, or they want to talk about how they can have more reusable mugs or more reusable items within the office space itself. So there's lots of different avenues they could go down.
Great, thank you very much. So thank you to the Green Team, Jeanette, Brian, Angelina, Noor. Now we're going to turn it over to the impact of bus idling at Rutgers. Dylan.
Dylan, whenever you're ready.
Yep. So hello everyone, my name is Dylan Scalo and I'm a senior studying mechanical engineering, and today I'll be discussing the effects of bus idling at Rutgers University. So motivation for this project started during my power plants class with Michael Muller, and he ended up pulling up the Department of Energy's annual energy flow chart. And when I was looking at the breakdown, I saw that transportation was the largest consumer of energy of all four sectors, consuming roughly about 28 quads of BTU in energy. And of this amount, almost 80% is wasted due to inefficiencies. So being a Rutgers student, this got me thinking of our own bus system and how it contributes to this 80%. From my countless interactions with Rutgers Bus System, I've been able to make three observations. The first one is that drivers leave the buses running while they're on breaks. They leave both doors open to allow students to continue getting on and off the bus, and they usually leave the HVAC system running continuously. And because of all three, fuel continues to be used by the engine and the HVAC system. So this fuel continues to be used while drivers are on their breaks. So I wanted to basically be able to see of how we can eliminate this and the fuel and CO2 emissions that could be saved from getting rid of bus idling. So I contacted the director of the Department of Transportation Services here at Rutgers, who was Dominic Rizzo, and he was able to provide me with the weekly schedule for buses, the fuel distribution amongst the bus fleet, and the habits of the drivers. Rutgers is actually unique in that 80% of its bus fleet uses a fuel called B20, which is a mixture of 80% diesel and 20% biofuel. This does help limit the amount of CO2 produced, but it also does result in less power being obtained from the engine. So if we look at figure 1, we can actually see the hour by hour distribution of the buses between a Monday and a Thursday. And this helps really emphasize the sheer size of our bus system, with up to 53 buses that operate at any given time during the peak time. He also said that formally their drivers are allowed a 1 10-minute break per shift, which for my report I estimate to be 3 hours. And I was able to use this statistic with figure 1 to find out the total amount of hours that were that the buses had over the academic year. I also had to get more specs about the bus themselves. So I found the vehicle identification number from one of the buses. And with it, I contacted El Dorado, California, which is the manufacturer for the buses. After talking with one of the employees, I was able to obtain a work order made by Rutgers back in 2010 for 38 buses, which helped me identify the HVAC system used in the buses and the dimensions for the bus. Along with researching the heat values for the diesel and B20 and the chemistry for them, I now have enough information to perform the calculations for the fuel usage and the CO2 emissions. So now if we go down to the results and the calculations, I just want to remind you is that I only looked at the idling that occurred during the 2018-2009 academic school year and did not include the winter and summer sessions. And I broke the calculations into two categories, one for the fuel consumed by the engine itself during idling and the fuel consumed by the HVAC system. So let's start with the HVAC system. From the the work order I got, the HVAC system uses a Thermo King, which draws 3.2 kilowatts of power to operate. So since it's drawing electricity, the engine has to use its alternator to convert the fuel into electricity. And through research, usually getting the fuel from its chemical state to its electrical state is only 20%, 21% efficient. So I was able to find the total amount of power drawn for the HVAC system and then multiply that by the heating value that you're getting from the field to get the total amount of energy that is required and that's wasted during the idling of the usage of the HVAC system. So I broke it down between the diesel and the B20 fuel and found that about a little under $7,000 is wasted in just the unneeded use of the HVAC system during the idling hours. Now, finding the amount of fuel that was used by the engine itself during idling, that was a little bit more easier. All I had to do was take the idling hours that was calculated from Figure 1. And I found a report from the Department of Energy saying that for transit buses, about 0.97 gallons are consumed per hour. So I took that number and multiplied it by the total idling times to get the total cost of fuel and the CO2 produced. Of course, these numbers are dependent on the fluctuating fuel costs. I mean, if I had done the calculations using the fuel prices today, these would be lower, but for the most part, I took what the average fuel cost was during the 2018-2019 academic year. So as you can see, the total amount of money that can be saved through bus idling is about a little under $25,000 in fuel. And you can also prevent about 90 tons of CO2 being produced, which is equivalent to 20 cars operating annually. Some of the future direction I was looking that I intended to do before the COVID-19 virus was to use an app called Translock Rider, which is an app that we Rutgers students use to live track the position of buses. And you can actually extract this data using Python, and you can kind of more accurately see how long buses are sitting idle in a location. So, of course, buses at stoplights are going to be idling, but you could put in the code for any time a bus is longer than like 2 minutes to count that as, to record that as an idling break. So Mr. Rizzo did say that a driver was allowed a 10-minute break per shift, but as a Rutgers students, we do see that I do believe that this is a higher amount of idling that's been occurred, and we can use Translock Rider to verify this. Another way that we can use Translock Rider is also to incorporate it in a driver's kind of dashboard to allow them to see the location of other buses so they can more accurately spread themselves along a route. Because what happens a lot is that bus drivers kind of throughout the day get congested with each other, and you'll have buses, like maybe 4 of the same bus on the route at the same bus stop. So by incorporating this inside the buses themselves, you can actually decrease idling at each stop by having them more efficiently spread out along a route. So I didn't do calculations for this because this is highly subjective, but this would be definitely a great implementation to get a more accurate depiction of bus idling time and the efficiency of the system itself. So as I said, some of the challenges with this implementation is that when you are turning off a bus during the break, I spoke with a driver saying that the lights and exterior lights will still be operational. However, the HVAC system will be turned off. So, of course, students' comfort is important. So I did some calculations saying that rather than the buses being both doors being open to the environment, only the front door should be to limit the amount of exterior air coming into the bus. And on a basic calculation, I only assume that within the 10 minutes, 25% of the air is being lost to the environment. And if you wanted to keep the inside cabin temperature about 5 plus or minus 5 of the desired temperature. HVAC system should only be turned on when the outside environment is plus or minus 20 degrees Fahrenheit than the desired temperature. So I did factor that assumption into my bus idling by analyzing some of the weather data of when the weather, the highs and lows were outside of that 20 degree range. The next thing just to see is that there are no capital costs that arise from this implementation because that these fuels use diesel, they use compression ignition, which means that there isn't really wear and tear on a spark plug because there is no spark plug. So there, even though you're more frequently starting up the vehicle, you aren't causing wear and tear on that component. So the only type of implementation cost that could come from this is the training that would just to have a new protocol to advise drivers to turn off their vehicles during the breaks. And also, if they wanted to incorporate the dashboard system to allow drivers to track where other bus drivers are on their route. But at the end of the day, is that I do think that this is a great implementation for Rutgers to implement. Because Rutgers does outsource their buses from a company called First Transit. The fuel savings don't directly go to Rutgers, but the CO2 emissions does, which is enough of an incentive because there's no capital cost to go along with it. But just to recap, is that just by turning off our bus systems during the breaks, we can save up to $25,000 of fuel and 90 tons of CO2 emissions.
Thank you, Dylan. Any quick questions? All right, it was very detailed. I appreciate it. Very interesting. So now let's go ahead.
There's a question in the chat.
Yeah. Okay. So I see it. So how does reducing idling impact the battery life of a bus? So with most cars and vehicles, usually the battery itself is charged while it's driving. So because it's only 10 minutes long, it would definitely, the light and exterior lighting would not be enough to kill a battery. And during its route of driving for at least 2 hours would be more than enough time to recharge the battery. So that shouldn't play too much of an effect in reducing the battery life.
Thank you again, Dylan. So next is establishing a greenhouse gas emission baseline. So Morgan, Treese, and Molly.
Hi, can everyone hear me?
Yes.
Perfect.
Yes.
Good afternoon. My name is Morgan Mark, and I am a sophomore majoring in environmental engineering.
Hi, I'm Therese, and I'm a junior majoring in marine biology.
I'm Molly, and I'm a junior majoring in physical oceanography.
And we will be presenting on establishing a greenhouse gas emissions baseline at Rutgers University, New Brunswick. Under our advisor, Dr. Rachel Schwalm, we use the Sustainability Indicator Management and Analysis Platform, or SIMAP, to analyze carbon dioxide emissions data collected by Rutgers faculty and vendors. Our emissions can be separated into 3 distinct categories: food systems, transportation, and energy in buildings. Food systems encompasses emissions from all of the processes involved in the life cycle of edible products purchased by Rutgers Dining Services. Transportation includes emissions from Rutgers-owned vehicles and any university-financed or affiliated travel. Energy in buildings describes the total emissions from Rutgers buildings and assets. By aggregating the data from these categories, one can see that Rutgers New Brunswick emitted nearly 35 gigagrams of carbon dioxide in the 2019 fiscal year, with energy in buildings contributing the most at 19.9 gigagrams, followed by transportation at 12.4 gigagrams, and finally food systems with 2 gigagrams. However, these figures may underestimate our total emissions because our team lacked necessary data. 2 ways to increase the validity of our findings are improving the data collection methods themselves and collecting measurements that are not already recorded. Some examples of this in practice are how there is currently no data about the energy efficiencies of specific buildings, whether food purchased is local or organic, or commuting patterns of faculty and students. Through the systematic approach outlined at the bottom, our group attempts to identify what information we currently need, what changes can be made, and the potential outcomes that can result from improved data collection.
The changes we need to make to create a greenhouse gas emissions baseline for Rutgers mostly revolve around changes in data collection. We need to prioritize building audits using cost-benefit analysis to understand which of our buildings are producing the most emissions and which should be prioritized in reducing emissions. We should also be prioritizing buying food from food vendors that document carbon emission-related data. It's difficult to know how much emissions are being produced by any given food source unless the vendor is directly reporting that to us. For transportation-related emissions, we need to collect data from faculty and students to learn about their commutes and Rutgers-related transportation needs to know the amount of emissions caused by transportation, especially from commuting, which we are lacking. And we could do this, for example, through surveys. In order to bring about even more change, we should be prioritizing educating students and faculty about different climate-related initiatives at Rutgers and involving them in the decision-making process. We're going to need cooperation from the Rutgers community in order to create an emissions baseline and ultimately become carbon neutral.
Overall, in order to reduce carbon emissions at Rutgers from these three crucial sectors, we need to fill in the data gaps that we've outlined to make an effective emissions reduction plan. The interim plan laid out by the President's Task Force does a good job of presenting some of these areas we need to focus in. And through our research, we can also see immediate areas of improvement. Eliminating outdated and inefficient gas-powered boilers and replacing with electric systems, incentivizing lower levels of commuting, and setting a standard on food vendors based off of their emissions profiles are actions we can take as we build up our baseline of data. And once the baseline of data is established, we can increase our understanding of exactly what components of these sectors are contributing to our emissions, as well as the most cost-effective way to reduce them. And in order to make this plan effective, it's crucial that the student body is aware of the current climate situation and the role that Rutgers plays. A more climate-aware populace will be able to support this plan through climate-positive behaviors such as carpooling, plant-based diets, and lower energy use in buildings. They will also more readily contribute to survey-based data that is crucial in understanding the behavioral patterns that dictate our transportation-related emissions. Thus, through taking action now on easily identifiable issues in these three sectors, collecting high-resolution data for the ultimate creation of a comprehensive action plan, and engaging an educated student body, we can move ourselves along the path towards carbon neutrality and make Rutgers a climate-resilient university.
Great, thank you very much. Questions? One while we're waiting for any from the chat. Of all the data you looked at, which set or subset of data do you think is the most important to get to the next level of detail?
Because energy in buildings has such a large percentage of our emissions, I think the most important subset is the aggregate data that we currently have for all of the buildings that are running off campus stationary sources. So all the buildings that aren't using the generation plant. So we have these aggregate numbers of like total energy consumption, but we don't know exactly how much fuel we're putting into individual buildings and the efficiency in those specific buildings.
Great, thank you. Any questions via chat? All right, thank you, Morgan, Teresa, and Molly. Up next is Alison on wind patterns. I'm sorry, there was a question in the chat, so I apologize for rushing that, from Rachel, so she's important. You note energy, buildings, food system, and transportation. Are there other sources of emissions not included in SIMMAP, I guess, in your analysis? Thank you, Rachel.
That are included in SIMMAP that aren't included in your analysis. I'm not sure if you guys know.
Thank you.
Yes, there are. So there are more sections that are included in SIMMAP than these three that we focused on. but we focused on these three sectors because they make up a majority of the emissions and because they pose the greatest opportunity for contributing more to the baseline and reducing emissions.
Excellent. All right. Now we're to Alison on wind patterns and offshore wind in New Jersey. Alison.
Hi, everyone. My name is Alison Pizaski, and I'm studying chemical engineering and will be graduating in a few weeks. For the last year, I've been researching offshore wind patterns and their effects on power prediction for the planned New Jersey offshore wind farm. So New Jersey is at the forefront of developing offshore wind energy with plans to create an 1,100 megawatt wind farm in the next few years. The NJBPU is currently working to develop, which will be the largest in the US when it's completed. It's important for wind developers to be able to accurately predict the power output in order to bid for available energy in advance. These predictions rely on weather modeling data and simulation tools. However, there are a few drawbacks to using weather models, which may at times fail to predict unexpected wind events, resulting in both over and under predictions of power output. Additionally, model data is usually analyzed at a few points within the wind energy area, which may not be representative of the whole region, and this can also cause mispredictions in power. For example, in figure 2, I don't know if you're able to zoom in a little bit on the bottom left of the screen. But in figure 2, we see wind speeds for the 3 months of summer 2019 compared at 2 different points in the wind area. The red bars correspond to the southern area shown by the red star in figure 4, and the gray bars represent the northern area seen with a green star. The histogram shows the variability in the number of hours at different wind speeds. Specifically in the middle area, when wind speeds are ranging from 4 to 10 meters per second, there are large discrepancies observed. The power curve for a 15 megawatt turbine is also shown here in black. Since power is a cubic function of wind speed, small changes in the speed will result in large changes in the power output. Figure 3 also further shows the magnitude of variability for power output at 2 different points in the wind energy area. Hence, evaluating wind speeds to predict power output at only one of these points would cause an over or under prediction of power for the whole area. So the purpose of this research project is to analyze the spatial variability within the wind energy area and determine what effect this will have on power prediction. In order to evaluate the spatial variability, hourly wind speed was obtained from the Rutgers University weather model, WRF. To ensure accuracy of the model, this data has been validated against observational data from buoys. The entire RU-WRF domain is shown in figure 4 with a black rectangle showing the specific area that was looked at in this study. In figure 5, we see the New Jersey wind energy area as the white shape with the dots representing the 3-kilometer grid points where the WRF data was obtained. So specifically, I looked at hourly wind data for the months of June through August 2019 due to the common occurrence of summer sea breeze and upwelling events during this time. The time and spatial variability was analyzed for wind speeds using an empirical orthogonal function in MATLAB. An EOF works by decomposing a data set into different modes of variability, both in time series and spatial patterns. A principal component analysis is also used to determine how the data set varies over time for each mode. This is an incredibly powerful tool in analyzing how these mode patterns represent the variability within the data set. Additionally, the wind data was interpolated to power output using a cubic power function for a 15 megawatt wind turbine, and a similar EOF analysis was performed with the power series. So the results for each EOF were plotted on a spatial map and compared to 2 buoy locations. We see a field station represented by a yellow marker and 2 floating light detection and ranging buoys, which measure the wind speeds, are shown in red on the 2 graphs on the bottom. The wind speed EOF is found to have a strong offshore-onshore variability in mode 1. So the wind speed, we have a strong offshore-onshore variability in mode 1, where the yellow color represents stronger overall wind speeds. This accounts for about 90% of the total variability. And overall, there's a history of stronger wind speeds offshore, which is consistent with the results we see here. In mode 2, however, there's a bimodal distribution present with this out-of-phase north-south relationship. This means that stronger winds in the north region will correspond with weaker winds in the south region and vice versa. And this accounts for only about 4% of the wind speed variability. Additionally, this north-south relationship seen in mode 2 could be a result of sea breeze circulation, which often causes uncertainty in the wind models as well. Additionally, the principal component of mode 2, which is the variability over time, appears to have slight fluctuations during sea breeze events, indicating higher spatial variability during these times. If you could zoom into the top right, like the discussion section. Thanks. So the wind power EOF exhibits a similar pattern as with the wind speeds, with higher power production further offshore. The second mode of the power EOF, which is not pictured here, exhibits a similar result as the wind, with that north-south bimodal distribution. Since power output is a function of wind speed, it makes sense that both of these EOF models exhibit similar patterns, indicating stronger modes offshore for mode 1 and an out-of-phase correlation for mode 2. However, when comparing power to the wind EOF, we see that there's actually more spatial variability with the power. This results in this high power area in the northeast section of the wind energy area. In this figure, we see that the F220 buoy lies in the highest power region on the map. So if we use observational wind data at this point, it'll result in significant overpredictions of power for the whole area. Meanwhile, the F230 buoy lies in an area associated with low power. So using data from this point would also not be an accurate power prediction for the whole area. So using observational data from only one point is not going to be representative. Because of this, it's important to look at both buoy and wharf model data along with the spatial distribution shown here in order to accurately assess the wind resource and predict power output. So in conclusion, based on the EOF analysis for both wind speed and power, we can confirm that the wind speeds indeed increase at further offshore distances, and that there's significant spatial variability within the wind energy area related to the weather patterns. This sort of analysis is useful to wind developers in order to determine how best to model the wind patterns and predict power output. So I'll be continuing with this research project over the next few months, where I'll be looking more closely at the relationship between sea breezes and the principal component mode variability. Additionally, I'll be performing a similar EOF analysis over longer time periods to gain a more accurate representation of the wind patterns year-round. Thank you all for listening, and I'll be happy to answer any questions.
Great, thanks, Alison. Any questions? Now, some of these posters are in response to the competition, and others are students have done, both undergraduates, over the last 12 months. So if there's any, that's Alison, in terms of the analysis you did, it was good to see you using PTA and other. Were there any surprises? What struck you at the end of your analysis that you weren't expecting when you started the project?
I guess I wasn't expecting to see such a significant variability. Like we knew that there's going to be some differences, but mainly in the power figure, we see that like there's this concentrated area of significantly higher power output. So I guess we did expect to see some variability, but it was surprising the magnitude with which we observed it.
Good. Any other questions?
So let me ask about the power output from the wind turbines. And in your figure 2, you showed that cubic response at lower wind speeds, and then it plateaus at high wind speeds. Obviously, that protects the equipment and everything. There's a now and they're sort of growing larger and larger turbines. They have larger outputs at that maximum. Would those larger turbines or different turbine sizes have a different slope in that cubic uprising region, or do they all overlap?
Yeah, so
wind data give you advice on which model to buy, for example, maybe install different equipment different places.
Yeah, so depending on the size of the turbine, here I used 15 megawatt because that's the only data I had available. I believe in New Jersey, they're putting up 12 megawatt. So each turbine would have its own power curve. So in that middle region, it wouldn't actually look exactly the same. The general shape would be similar, but the numbers would be different depending on, the specific model of the turbine.
Great. There's one question from the chat, and then we'll move on. What is the frequency of wind damage to the turbines, and is there evidence that particular designs are at fault? That may be premature in terms of they haven't been built yet, at least off the U.S. coast. But Alison, any thoughts on that? Or
So I haven't looked into the specific wind turbines yet. There is definitely damage that occurs, especially at very high wind speeds. But I know one feature that they have to protect is that the wind turbine will actually shut down if it exceeds like the maximum speed. So it won't, it won't be running constantly. If there's a high risk of damage, I know they, shut it down and they'll weather the blade so it's not going to sustain as much damage.
Great, thank you very much, Alison. Up next is Stamatis and Gian. They're going to talk about outage modeling in power systems.
Hello, everyone. Should I present my screen? Okay. Yes, yes. Okay, great. Now I can see. Okay, hello, everyone. Thank you very much for being here. My name is Stamatis Tsianikas, and today I will presenting you a joint work that I've done with my group, Nusin Yousefi, Gian Zhu, and Professor David Coyd. I am a PhD student at the Industrial and Systems Engineering Department at Rutgers, and probably this is going to be my last year. So today I'm going to speak about outage modeling in power planning systems, and we are going to focus in a problem called generation expansion planning in power systems. So first, let me give you an introduction on what this problem is about. So expansion planning problems refer to the monetary and investment and unit investment regarding energy production and storage. And specifically, we studied the case of microgrid. So the problem is, given a microgrid, specific facilities that it is required to serve, specific power plants and storage units, what is the optimal plan, the optimal policy that we should follow in order to expand the storage capacity on this microgrid. Now, the main problem is that we have stochasticity in almost every element of this kind of problems. We have stochasticity in the generation output of renewables. We have a stochasticity in the load demand, in the climate change. And specifically, the kind of stochasticity that I'm going to talk about today is the frequency and duration of outages. So how do we think about outages, how we can model them optimally in our models, and how the optimization results are affected by the outage modeling that will follow. Now, why is this so important? For the motivation of the problem, we should say that, especially in microgrids that are required to serve facilities like hospitals or other critical facilities, this is a very important aspect because it will affect the reliability of these facilities. The hospital nowadays, they have electronic equipment like blood storage, very life important machinery, etc. So they require uninterrupted service. In most of the current studies to the literature so far, what we've seen in terms of modeling the outages is usually they are modeled by a single statistical distribution, and most of the time this is a Poisson process. In this study, I am going to show you an alternative modeling that we propose, which is basically a superposed Poisson process. I'm going to talk about it in a few. And this is based on the premise that the outages are not coming from a single distribution, but instead they are coming from two different distinct distributions. And let's call them for now regular and severe. As I said, the baseline problem that we're trying to solve is an expansion planning problem. So we want to derive optimal policies for a finite horizon time. It means which storage units should we choose, when should we decide to install them, and how much capacity should we add in our microgrid, in our system. So this is basically a sequential, I would say, investment planning framework for storage. We will attempt to solve this problem using Markov decision processes and reinforcement learning, and I'm going to give you the definition in a few. And finally, the thing that we would like at this point to focus on is the difference between the two outage models, the single Poisson process and the superposed Poisson process. So first of all, let me give you an introduction in MDPs and reinforcement learning in the methodology section. in order to formulate our problem as an MDP. So what is basically an MDP? It's a Markov chain. It's a stochastic process that resembles like a Markov chain, but here we have actions, rewards. So the basic components in an MDP are the agent and the environment. The agent should take actions. The environment, given these actions, should transit the system to a new state and should produce a reward. And now the goal of the agent is to observe these rewards and derive an optimal policy throughout the whole finite horizon. And when I say optimal policy, here we have to take into account delayed rewards, rewards that won't come immediately, but will come in subsequent periods. And why is this important? Because when we decide to invest in a storage unit, in a microgrid, probably the investment cost, the upfront cost that we have to pay is significantly higher than the savings that we'll have. The savings that we'll have correspond to the loss of load cost that we'll need to reduce, right? But this will come at a later period. So it's important to account for delayed rewards. Now, why is it important and what was our motivation in order to construct this alternative scheme that I said before, the superposed Poisson process? If we look in table 1, in the KD data provided by the New York State for the company of PAC and Long Island for the years 2012 to 2017. So what we're seeing here is an indicator called KD, Customer Average Duration Interruption Duration Index. This is basically, in simple terms, the average duration of an outage, of an interruption for the whole year, right? If we see the data here, it seems that the data from the years 2013 to 2017, maybe we could say that they're coming from the same distribution. However, the average interruption index for the year 2012 was close to 23 hours, much farther. It was clearly an outlier compared to the other values. So that was our motivation. And this number probably stems from the fact that in year 2012 we had Hurricane Sandy, which affected like 70 million or maybe more population in the whole US. We had outages that lasted a day or even longer, and that's why we are seeing this number over there. And that was our clear motivation on building this alternative scheme. So what is this scheme? First of all, if we consider a single Poisson process, we have a single rate lambda and the number of outages at any time t follow Poisson distribution with a rate lambda t. If we consider this alternative superposed Poisson process scheme, we have two distinct Poisson processes. One with a rate lambda 1 for the regular events, and the other one with rate lambda 2 for the severe outage events. And of course, afterwards, we can define the probability that an outage coming from this superposed Poisson process comes from the regular Poisson process or the severe Poisson process. In our case study, if we take figure 1, we will see how these two alternative schemes change the distribution of the outages. And what we're seeing here is the probability that a specific outage will have a corresponding duration in hours. And as you will see, in figure 1a, most of the outages have a mean around 5 and the variance is equally distributed around 5. However, in the second scheme, because we'll have this in figure 1b, because we have the Poisson process, have outages. Most of the outages are short-lived, we would say, but we have also some outages which could be potentially catastrophic. And this is a very important part in our work. These outages happening around 20 to 25 hours in figure 1b. So the mean duration is the same, but the distribution is not. And our goal is to study how this distribution change will affect the optimization results. Now, for our case study, we studied a microgrid in West Hampton, New York, and we got real data, location-specific data, meteorological and load demand data. We consider microgrids of these facilities that I have in my numerical assumptions, 2 hospitals, 5 schools, 300 residential facilities. The storage options that the planner has is basically 4. We can invest in lithium-ion batteries, lead acid, vanadium redox batteries, and flywheel storage. So we don't have only electrochemical batteries, but we have some other sorts of storage units for options. And the considered stochastic component is the price. So basically, we observe price changes affect the optimization results too. In the results section, what I'm going to show you and what I want to show you is the results of two experiments, two identical experiments. We ran two identical experiments. The only parameter that we changed was the outage model that we used. So I will not give you all the numerical assumptions, detailed numerical assumptions, because again, we are comparing, we try to be fair in our comparison and use only different outage models, outage model. So the storage unit prices were declining for both scenarios, and we observed that the optimal policies differ significantly, although all the other parameters remain the same, just because we changed the way that we perceived outages and we felt about outages and we modeled outages, we saw different policies. So let's see the results. In the single portion process, first of all, we have 7,000 kilowatt hours total storage capacity after 4 decision periods. So what we see here is the results for both the single and the superposed portion process. The blue color corresponds to the single portion process. The orange corresponds to the superposed one. So if we see only the blue, we'll see that we have 7,000 kilowatt hours total storage capacity. If we see the orange, we'll see that we have only 4,000 kilowatt hours total storage capacity installed. So this is the first main difference. The second main difference is that the first investment happens 1 period earlier in the single portion process scenario. So maybe it means that if we think about the single portion process, it's more urgent for us to invest in storage in our microgrid. If we try to interpret these results, we would say that the portion process scenario, the vast majority of outages are short-lived, as we said before. They are not long-lasting, and therefore they could be handled with, first of all, the renewable plants that I may have in my microgrid and a moderate amount of shortage capacity. In the case of the single portion process, though, most of the outages last more than or around 5 hours. So that is the reason I would need more storage capacity in my system. The thing that could worry us is that in the superposed portion process scenario, the optimization results show that we probably do not have a plan how to handle these catastrophic events. And we should specifically...
Try to wrap up, please.
Okay, sure. We specifically model and take steps towards addressing these catastrophic events outages. So the focus of this study was to highlight the importance of analytical and proper outage modeling, specifically tailored for microgrid applications. And the open research question is to further study how to deal and handle these catastrophic events. Thank you very much for your attention.
Great. Thank you. Any questions?
So this is Dunbar. Let me first say really nice work in trying to tease out these 100-year catastrophic kind of occurrences separate from a normal windstorm or whatever outage. I would wonder in your formulation of the value of lost load when you have an outage, whether you might also have different value of lost load for a catastrophic event than for a short outage. And let me explain in some ways. At home, if I have an outage for 2 hours, then the food in my refrigerator doesn't spoil. It stays cold enough to be not damaged. So the value to me is different than if I have an outage for a week and I have to throw away a lot of food. Different, that's maybe a minor point compared to what a factory or some other outages might be.
That's a great question. So actually for the value of lost load, we used a study that predicted value of lost loads for the year 2030. And we wanted to use a forecast instead of some real numbers for 2 reasons. First of all, for the forecast, because we are working in 20 years ahead. So we wanted to use numbers for 20 years ahead. And also because we don't have actually, we haven't properly quantified what is the value of lost load. And now to answer your question, we use different value of lost loads for different facilities, but this is increasing with the duration outage. But that's a very interesting idea. What we first thought was that maybe value of lost load should be increasing as the years go by. So because there's an electrified future ahead of us, right? We're using equipment more and more in our facilities, even if it's a hospital or if an office or a residential facility. So maybe the value of lost load should be increasing with time, but I think that's a good observation. Maybe we could model the value of lost load to be an increasing function of the outage duration. But again, it would depend on the facility.
Yeah, there has been, this is Frank, there has been some work, mainly coming out of Sandy, to report value of lost load across the duration as well to try to accommodate the point that Dunbar made. Excellent. So now we're going to turn to Pranay Kumar, who's going to talk about behavioral interventions in the food, energy, and water nexus. So Pranay.
Thank you, Professor. Can you all hear me okay?
Yes.
Hello, everyone. My name is Pranay Kumar, and I am a PhD student at the Blaustein School of Planning and Public Policy. And my presentation is on evaluating spillovers from behavioral interventions in food, energy, and water conservation based on a systems approach. And this is part of my ongoing research work under the guidance and supervision of Dr. Frank Felder, Dr. Rachel Schwamm, and Dr. Kara Quitty. So as the role and potential of behavioral interventions is catching attention of policymakers in the food, energy, water consumption, it is becoming important to evaluate the impacts of such policies for their effectiveness. In my presentation, I'll be briefly touching upon the issues and challenges associated with evaluating spillovers from behavioral interventions for food, energy, water conservation. And thereafter, I'll give an overview of the proposed framework for evaluation of spillovers based on a systems approach. But before that, just a few definitions. So what exactly is spillover? So spillover has got different names: knock-on effect, spin-off effects, catalyst behavior, rebound effects, foot in the door effects, etc. And there are the most commonly used definition of a spillover is that of an effect of an intervention on subsequent behaviors which are not targeted by the intervention. And then there is a separate definition of behavioral spillover as an observable and causal effect that a change in behavior one has on a different subsequent behavior. So why are we studying spillover, as it is an important metric in the impact evaluation, and failure to account for a spillover leaves out valuable information, and it also might result in biased and underestimates depending upon the context. Spillovers have been studied across different disciplines ranging from economics, marketing, health, law, physical, and social sciences. And broadly, it has been categorized as positive or negative. And then there are underlying theories supporting one or the other, but there are other types of spillovers as well. So the most commonly adopted approach for measuring spillovers is based on randomized controlled trials in which a control and treatment group is subject to interventions, and then the changes in behavior 1 and behavior 2 are measured separately for the control and treatment groups, and the difference is taken to evaluate the spillovers. But that is not all, as we can see from my schematic explanation, that once we talk of behavioral spillover, the definition says that there is a cause and effect relationship between the two behaviors, that is, change in behavior 1 leads to change in behavior 2. But normally when we measure the behavioral interventions, we normally give an intervention first, and then we measure the changes in behavior 1 and changes in behavior 2. For an example, if we are trying to assess the spillover in terms of use of plastic bags or use of paper bags, and we try to give a message for saving energy. So saving energy becomes change in behavior 1, and then it can lead to some subsequent changes in behavior, for example, avoiding use of plastic bags and things like that. So there is a subtle distinction between the measurement and definition parts of it, and that leaves out the possibility of intervention leading to changes in behavior 1 and changes in behavior 2 simultaneously. And that could be one of the possible reasons that the change in behavior 2 may not be a result of change in behavior 1. It could be the result of intervention as such. So there are issues and challenges which are associated with the measurement of spillover. And most of the studies conducted to assess spillover effects explore the nature and direction of causal relationship between behaviors, and they rely on the estimation of gross effects from one-time behavioral intervention for conservation of food, energy, or water sectors in isolation. And in that case, it is very difficult to model, isolate, and measure the impacts in a noisy real-world setting in which a lot of things are happening at the same time. So, and also there could be possible existence of multifaceted relationships between behaviors rather than a linear cause and effect, single cause and effect relationship. And especially when we think of in terms of the greenhouse gas emissions and measuring the impact of human behavioral interventions, the greenhouse gas emissions and climate change are subject to uncertainties, in which the uncertainty itself is uncertain. So that in that context, my research question involves how to design a testable evaluation framework for behavioral interventions for food, energy, and water consumption. And the second question is how to evaluate spillovers from behavioral interventions in a noisy real-world setting. And we have relied on the systems concept, which is not something new, but it involves three core concepts of understanding interconnections and understanding the multiple perspectives and the boundary judgments. And for those of you who are like me and not able to understand what this picture is all about, so that is system concepts involves connecting the dots to look at the bigger picture and identifying the pattern. For example, in this picture, it is that of a Dalmatian dog, which when we look at it carefully, it is sniffing the ground. So just to give an idea that system concepts involve connecting the dots or the identifying the pattern from the individual activities and the individual cause and effect relationships. So based on this system concept, we have proposed a framework which involves system boundaries, context, and interactions. And one example, as we can see in the picture, can be in the figure 2, can be a residential. Instead of concentrating on an individual cause and effect relationship between behaviors, we can think of an intervention for a residential household as a unit, as a system. And then the food, energy, and water conservation behaviors could be a targeted behavior. And then we can think of assessing spillovers behaviors across settings and domains. For example, we can look at the driving techniques, or we can look at biking behaviors, or across the settings, we can look at the office consumption of energy and things like that. So it could be measured across the settings and domains. And then we need to identify the evaluation criteria as to what are the, for example, there could be 6 evaluation criteria. What are the criteria? Accordingly, we can design the interventions. And the spillovers could be across different geographical regions and cultural settings. So we could examine across the residential units we can compare with respect to the office and the residence behavior, or we could compare with respect to different geographical regions. And there are a lot of theories underlying the positive and negative spillover behaviors. So one possible option could be to evaluate the net effects of the intervention. So for example, we can take the sum of the positive and negative and trying to find out the net impact of the effects rather than concentrating on one specific positive or negative spillover behaviors. And then steps involving the life cycle assessment of greenhouse gas emissions for the entire supply chain instead of concentrating on a temporal activity. And then finally, of course, mentioning the limitations and constraints of the experiment upfront should give rise to a better evaluation framework. So I think this is all I have with my presentation, and I would be happy to take any questions.
Great. Thank you, Prene. Thank you. Any questions from the chat room? A quick question. I know it's come up with your work with Rachel. You guys have been out doing surveys, or there's a series of surveys. Just briefly, how's the COVID-19? What are some of your thoughts, at least one or two, on how this will intersect with your efforts?
Yeah, so for to this COVID-19 thing, our survey has not hit the ground in its original form. So there is a slight change in the question format, and that based on the results, we will be further evaluating the spillovers and other, of course, other project parameters.
Great. Oh, a question from Gene Fox. Pranay, who do you think will be most interested in this research? Governments, electric distribution companies, or energy distribution companies?
Yeah, that's a very good question, actually. Normally, when we think of the energy conservation, we think of in terms of the price-based instruments. For example, we think in terms of the carbon taxes or the cap and trade arrangements, things like that. But recently, there is an thought on the behavioral interventions also. So, for example, when in fact in this country also, it is very difficult to come out with taxation, carbon taxation, or any cap and trade policies at a national or at a very bigger level. So we can think in terms of the incremental policy aspects involving the behavioral interventions, and these are also very cost effective. But at the same time, the evaluation of such policies are very difficult, and there are issues involved. So this policy can be adopted at the government level, as well as the private governance level. So that is what I think of, but there are issues involved, so that needs to be studied further.
Excellent. Thank you. And then in our final yeah, very good. Thank you. Our final presentation by Petros on, we're back to offshore wind and maintenance. So that will be a good playoff from the analysis of wind speeds and wind characterizations that Alison did.
Exactly. Thank you. Hello, everyone. I'm a first-year PhD student at Rutgers Systems Engineering. And this is a work about opportunistic maintenance for offshore wind farms, a work that involves also Professor David Coit and Ahmed Azizat. So let's go to the introduction first. So our motivation for to make an optimization model for opportunistic maintenance in offshore wind farms, mainly that wind energy will contribute highly in 2050. It will the contribution will increase by almost 500% from 7.3% that is today. So currently operations and maintenance tasks account for about 30% of total operational expenditures in offshore wind farms, which is highly greater than an onshore wind farm counterpart. And that is mainly because, except for high winds that really damage the wind turbines, as we mentioned earlier, it could also be because there is limited accessibility into the wind farm's location, since they are usually located dozens of miles off the shores. Also, they usually have nominal capacity, so turning them off during maintenance would mean that we lose too much revenue. So we have high production losses. And also there are many safety considerations that we need to consider because due to weather meteorological conditions. So the industrial practice in offshore wind maintenance is usually either reactive or time-based. So they either not wait, but the turbine usually fails first, and then it is maintained afterwards, corrective maintenance, or it is time-based, like they have scheduled plans, pre-scheduled times where they are going to make the maintenance, and this is how they do it. So our take, the opportunistic maintenance would be in the literature is either to tackle any of the three previous, the aforementioned contributors of the high operational and maintenance costs. So our approach into opportunistic maintenance is to create a mixed integer linear program to tackle all those three issues into a unified and into a holistic approach. So we're trying to group maintenance to schedule maintenances during low wind periods, and considering consider site accessibility to also ensure on-time completion of the tasks. So we do that by creating this mixed integer linear program, whose objective is to maximize the total profit of the wind farm during a pre-specified period that we wish to make the scheduling. To do that, we discretize the time framework into a short-term horizon, where we consider hourly intervals from, for example, from hour 1 to hour 24. And this is for the day ahead planning. So this is for the plan of the next day, and it is in hourly intervals. And we also have the long-term horizon, where we take the rest of the period, of the remaining period, where we want to make those maintenances, and use them in hourly intervals. And for two main reasons. First of all, to alleviate the computational burden of the optimization, and also to account for our limited knowledge for meteorological conditions after the first day, after the day ahead, because this model is deterministic as of now. So as we see, this is the objective function, the first equation. And the short-term profits, actually, they are comprised of the revenue. The profit is the revenue. And we subtract from this value the maintenance costs. We also consider crew hourly payments. And there is also the vessel rental and the overtime pay. And so, and almost the same for the long-term profit. And we also consider other constraints such as crew access, turbine accessibility, etc. So to illustrate how the model, we created a case study. Oops. Yeah. Okay. We are considering a case study where we use 10 5-megawatt wind turbines, and we use meteorological data from Nicerda's buoy, the same buoy that was used in in one of the previous posters, was located off the coast of New Jersey. And we also use power data from an operational wind farm in the US. And we perform a binning method to calculate the amount of power that is going to be produced from the weather data that we got from Nicerda. So for this case study, we consider a maintenance task that requires, first of all, access to the nacelle, to the turbine's nacelle, and a medium-sized vessel to transfer the maintenance crew. So for these reasons, we also consider the accessibility to the turbine, and the turbine is not accessible if the wave heights are greater than 1.5 meters, and if the wind speed is greater than 15 meters per second. So we see on the first, on the three graphs below, the weather profile for those, we consider 16 days. In the blue line, we see the wind speed, and the red line, we see the wave height. And if those attributes they go above the safety limits, then we say that the turbine is inaccessible during that time, having a red background when this happens. And if it's below, then we say it's accessible. On the middle, the power level throughout our whole period. And on the third diagram, we see the actual output of the model, which is the schedule. that is going to be used. So we have the residual life estimates for each wind turbine, which we consider that we already know. And we see that we have preventive maintenances and corrective maintenance. Okay, so the main results I would like to focus for this study are, first of all, the computational results. So we managed to create this mixed integer linear program, which is solved in GAMS in a standard laptop using IBM Cplex. And for almost every result, we get solution time, which is in less than 30 seconds and has an optimality gap of less than 0.1%, which is a very good, very efficient model, computationally wise. So, and we also wanted to compare the actual savings that it would have from this model. So we consider three strategies. First of all, non-opportunistic. So we consider no accessibility and no vessel dispatch costs. And the two strategies followed by industry, which is time-based and reactive. And we solved for each for our model and for the benchmarks. We solved for 80 different weather profiles, so to get a view of the variability of the cost. So as we see in the first bar chart, our model most times performs better, produces better total costs. And if we go to the second bar chart, we see that in each for each single instant weather profile, our produces always the best solution. And we see an average increase of 20% in total costs for the non-opportunistic model, and 50% and 200% for time-based and reactive maintenance, respectively. So the model that we presented is both cost efficient and computational efficient. And we managed to highlight the importance of following an opportunistic strategy in offshore wind energy. So thank you very much. This is my poster presentation.
Thank you, Petros.
Yeah.
There's some questions about the wind speed, but I suggest talking to Joe Brody offline if you're interested in the distribution of wind speeds across seasons and time of day, because I know those guys have done a lot. But Petros, off the top of your head, do you have a sense, and of course we really won't know until we actually build the wind farms, but roughly what are the assumptions of how often planned maintenance is done in a year, and roughly on average how many days a year, or what percent is a turbine down just due to planned maintenance, if you have a sense of that?
Yeah, sure. Well, first of all, yeah, maintenance is it's very, there is no standard like format in how we, well, okay, turbines usually fail maybe once per year. In this study, we assume that we have a health monitoring system that tracks down and gives a deterministic residual life estimate for a series of turbines. Other than that, in the literature, yes, that each turbine may take, usually they fail, they require maintenance once or twice or thrice per year. But I don't know if this answers your question, but
yeah,
maybe if it didn't, maybe if you could ask me again, because.
A quick follow-up, someone else in the chat room has a question about in terms of how does preventive maintenance perform in respect to cost. So I guess the question is, you know,
how much does the preventive maintenance cost? Basically.
Yeah, and then there's also the avoided cost. You know, that's the expenditure side, but there's a benefit, the cost of not having a windmill down, a turbine down.
Right. Okay. Yeah. So the preventive maintenance, we in this case study we say that it's a like it's an oiling of the gearbox or likewise. So we assume that it's costs about $4,000. And we also we say for that if the corrective maintenance is not performed on time, then the turbine will fail and will require corrective maintenance after that. So we assume that if the residual life is surpassed, then the turbine will deterministically fail, will not produce any revenue throughout the time that it's offline. And the corrective maintenance is also more expensive. In this case study, we say that it's 4 times more expensive than the preventive maintenance. So $16,000.
Okay. And Brody, I don't know if, not to put you on the spot, but in maybe, I know it's hard to do in 2 to 4 sentences, 3 to 5 sentences, just a quick summary of the wind characterizations over time and season, if you're out there, Joe.
I could say, can you guys hear me okay? Sorry.
Yes.
Yeah, so I mean, there's definitely variability both with time and season. Sorry, I missed some of that discussion. I was checking a couple emails. I mean, overall, the further offshore you get, the stronger the winds get, and then the stronger winds are in the winter than it is over the summer. I mean, that's kind of just a broad statement, I guess I could make. But yeah, we have plenty of model data and we've worked with, we've already been working with Ahmad a bit on some stuff. So, I think you guys already are familiar a little bit with the kind of data that we have from the model.
Yeah, and those reports and data are out on your website, and I assume people can reach out to you if they, probably too much information is out there, and since if someone just wanted a high-level response.
So are you talking to? Yeah, I'll be happy to answer any questions. I have my email in the poster. I'll be happy to answer any questions. Yeah, definitely.
And I think I successfully recorded most of this, despite being told 3 times hit the record button. I messed it up somehow. So that we'll get this in the next couple of days posted, and along with probably a PDF of all the posters, so people can look at them individually without having to kind of navigate through the partial recording. Let me just see real quick if we missed anything, any final questions, or obviously if you think of them offline, you can send me an email. I'll give people 30 seconds to type in their life's work in the chat box. But any final questions or comments from anyone? Hopefully this was helpful. If you do have feedback, let us know, because we may be moving towards this world more and more down the road. So any feedback would be grateful.
Can you recap when the energy contest students will hear back about the results?
Yeah, probably in about 2 weeks. I just want to give some time because folks are, Dunbar, Rachel, Kevin, Lyons, and myself, we're finalizing like student grading. So I want to hope to do that in the next 2 weeks, but something like that. But once we set up a schedule, I'll let folks know. Thank you, Preeti. All right. Anything else? If not, thank you very much, and have a good day.